And now it's time to talk about the fundamental theorem of calculus, or in other words, the most important theorem of calculus. So there's actually two parts to the fundamental theorem of calculus. Both of them are fascinating. One goes like this. Suppose that you find the antiderivative of a function. So in other words, what function is it that you would take the derivative of and the answer would be x squared? Well, we do this with adding 1 to the exponent, which makes it a 3, and then divide by that. X to the 3 over 3, and then plus c. Then the good thing with antiderivatives is you can check your answer. So now take the derivative of x cubed over 3 plus c. And when you take the derivative using the power rule, the 3 goes in front. It's going to cancel this. Subtract 1 from the exponent, it leaves x squared. And the derivative of a constant is 0, so the answer is x squared. So when you integrate a function, and then you take the derivative of that answer, you get the original function back again. So in other words, derivative and integrals are actually the opposite of each other. Much like if you take the square root of 3 squared, you just get the 3 back again. All right, for the second part, suppose you look at the graph of x squared. Nice little parabola right here. And then we find the area from 0 to 1. So, in other words, find this area right here. So we could take this interval and then divide it into 100 pieces and then add up all the little rectangles to find the area. I feel like we've done that enough. Let's try it this way. So first of all, with the calculator. So graph x squared, and you can just go to zoom standard. Draws a nice little parabola. And then go second calculate number 7 to find the area and go from 0 to 1. And it says that the answer is 1/3. Now let's do that without a calculator. And it goes back to this idea, believe it or not. So looking at this, you might think that has nothing to do with the area, but check out this magic. So then integrate x squared from 0 to 1. So first, find the antiderivative. I found it, it's right there. X cubed over 3. Now for this, we're just going to get a number as an answer, so we're not going to get a plus c, so this, you don't need to put the plus c. After you've found the antiderivative, then instead of having this integral symbol, you put a straight line afterwards and say it goes from 0 to 1. Substitute the top number first, so that's going to be 1/3 over 3 minus, substitute the bottom number, that's going to be 0 cubed over 3. And when you reduce all of this, it turns out to be 1/3. It tells you the area. So these are the two parts of the fundamental theorem of calculus. The integral and the derivative are the opposite of each other. They'll cancel each other out. Also, if for that x squared function, you want to know the area underneath the curve, it's actually the antiderivative that will tell you the area. And it's not an estimate, it is the exact area. Mind blown. So for example number 2, so this is called a definite integral. So you have a definite starting place and a definite ending place. How about if the function is e to the x? So the first thing to do is find the antiderivative. And the antiderivative of e to the x is e to the x. And then you put the straight line after that and go from -1 to +1. And just like when you wash windows, you start at the top first and then work your way down. So this is going to be e to the 1 minus e to the negative 1. So you could leave that as e minus 1 over e. That would be the exact answer. Or if you want a decimal, you can go e to the 1 minus e to the negative 1. And as a decimal, it's 2.350. Now let's check and make sure that I actually got it right. So graph e to the x. And you can just go to zoom standard. As long as the x-axis includes the negative 1 and positive 1, that's going to be good enough. Then you can go second calculate, go down to number 7, and then go from negative 1 to positive 1, and it shades the area, and it says that is 2.350. For example number 3, what if we integrate from 0 to pi and it's sine of 2x? So first, find the antiderivative. Well, I know that the derivative of cosine is negative sine, so the answer here for the antiderivative is going to be negative cosine of 2x. That way, when you take the derivative of cosine, that will be negative sine. Then that negative will cancel that negative and just give you positive sine. Now there's one other part, because if I check my answer, I know that the positive sine part's correct because I just checked that. But if you're taking the derivative of this, then eventually you'd have to take the derivative of 2x, which would put a little 2 on the outside from the chain rule. Since we don't have a little 2 on the outside, for this one what we have to do is compensate by dividing by 2. And then evaluate that from 0 to pi. So that's going to be negative cosine of 2 pi over 2 minus negative cosine of 0 divided by 2. Let's see, cosine of 2 pi. So cosine starts at 1, goes down, goes back up to 1. So this is actually equal to 1. But because of that, it's going to be negative 1/2. And then a negative times a negative is a positive. Cosine of 0 is 1. And so this is 1/2. And a negative 1/2 and a positive 1/2, it equals 0. So how could it be that the area equals 0? Vamos a ver. If you graph the original function, which was sine of 2x, and you change the window to go from 0 to pi, and I can change the y's to range from negative 1 to positive 1 since we're talking about the sine function. And then take a look at the graph. So this part right here counts as positive area, and this part counts as negative. And they're symmetric, so whatever this equals, it's positive, whatever that equals, it's negative, and they cancel each other out. So we get 0. Now, the function just said, the question just said integrate from 0 to pi, and whatever you get, that's the answer. If the question said find the area between sine of x and the x-axis, then what we'd do is integrate from here to pi over 2, find out what that area is, and then double the answer. But this one just said integrate, so we get 0. Example number 4. How about if you integrate from 0 to 2, and it's x plus 3 times x minus 5. So find the antiderivative. Notice that this up in here is a product, and we have not covered the product rule for integrating yet. So we cannot use that. Instead, we're going to have to do algebra and actually multiply this out ourselves. Or actually myself, and then you can follow along. Anyway, x times x will be x squared. For the middle term, this would be negative 5x. This would be positive 3x. That leaves negative 2x. And then a 3 times negative 5. Okay, then find the antiderivative. So this one will be x to the 3 over 3. Right now this one's exponent is a 1, so it's going to become x to the 2 over 2, and then the 2's will get cancelled, so it's x squared. And then minus 15x. Evaluate that from 0 to 2. So this is going to be 2 cubed over 3 minus 2 squared minus 15 times 2. And then when you substitute a 0, that'll be 0, 0, and 0. So this 0 does not contribute anything to the answer. So let's see, this is 8/3 minus 4 minus 30. Eight thirds minus 4 minus 30 is negative 31.333. And now check the answer. So I would always graph the original function. Don't even graph that, because if I made a mistake in the algebra, that's the whole reason I'm checking it right now. So check the original problem. Parentheses x plus 3 times parentheses x minus 5. And then the window needs to include at least from 0 to 2. I'm just going to go zoom standard. Oh, now I see why the answer is negative, because it's way under here, underneath the x-axis. Then calculate number 7, the integral from 0 to 2. And it says you should have gotten negative 31.333. Let's see if I have enough space to do this one. Example number 5. Integrate from 0 to 9 the square root of x. So what's the antiderivative of the square root of x? Well, what I'm going to do is rewrite it as x to the 1/2. And then add 1 to the exponent. That's going to make it 3/2, and divide by 3/2. So this you need to invert and multiply by 2/3, and then it's going to be x to the 3/2 power, and then evaluate that from 0 to 9. So substituting the 9 means there's going to be 9 raised to the 3/2 power, and then minus 2/3, and 0 is raised to the 3/2 power. This, of course, is 0. This means take the square root of it. So taking the square root is going to be a 3, and then cube that, which is 27. So it's 2/3 of 27. And then a 3 will divide into 27 9 times, and 9 times 2 is 18. Should we check it? All right, sounds like a good idea. So the square root, that's not square root. Hey, the square root of x. And then this window definitely goes from 0 to 9, so that's going to be good. And then second calculate, number 7. What's the area from 0 to 9? Calculator thinks that the answer is 18. Oh wait, it is. Good job, calculator. Job, buddy. And example number 6. What about the integral from 1 to 2, and it's x squared plus x plus 1. And then the whole thing is divided by x. So this one is a quotient, and there isn't actually a quotient rule for integrating, so we can't use any type of quotient rule. Instead, what we're going to have to do is algebra. So basically this is saying the whole top part gets divided by x. That also means each individual one in the numerator gets divided by x. Or in other words, you could break it up into 3 fractions. One says x squared over x. The middle one will say x over x. The third one will be 1 over x. And then I should even reduce those, so the first one will just be x, the middle term is a 1, and the last one is just 1 over x. Now find the antiderivatives. This one's exponent is a 1, so add 1, that's going to be x squared over 2. The antiderivative of 1 is just an x. And then the antiderivative for 1 over x, that's going to be the natural log of x. And remember, when we have numbers to plug in, there is no plus c. So then it's going to be evaluated from 1 to 2. And which number do I plug in first, the 1 or the 2? You're right, it's the top number. Always start with the top number. So this will be 2 squared over 2 plus 2 plus natural log of 2. And then minus, and then everything after the minus should be in parentheses. 1 squared over 2 plus 1 plus natural log of 1. So how much is this? This would be 4, but cut it in half so that means it's 2. And 2 plus 2 will be 4. And then this is minus 1.5. So how much is 4 minus 1.5? 2.5. The natural log of 1 is 0, so that I don't need to pay attention to. And then there would be plus the natural log of 2. Or as a decimal answer, that's going to be 2.5. Need to watch while I'm typing. Plus the natural log of 2, and the decimal answer, 3.193. So do you trust that I got it right, or should I check it? You're right, check it. So the original problem, x squared plus x plus 1. That gets divided by x. Then go to the graph, makes this beautiful little hyperbola looking shape. And then second calculate number 7, go from 1 to 2. And is the answer 3.193? Oh, Bob's your uncle. 3.193. Ding, 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 ding. Okay, so like I said, there's 2 parts to the fundamental theorem of calculus. One is, if you need to find the area under the curve, use the antiderivative, plug in the top number first, then the bottom, subtract them, and you're done. That's how you find area. It was fun finding area with those rectangles and the sum sequence and all that, but it's sort of cumbersome. This is the real way to do it. Now the other idea is that the derivative and the integral are opposites of each other. So we need to do a couple of examples like that. So for example, number 7. So if I set up an integral, and then later I'm going to take the derivative with respect to x. Then in here, I can't use x because this integral has to be a function of x, and to make it a function of x, what you do is you have the limits go from 0 to x. So then what that is saying is go from 0 out to x, and whatever the function is that I'm going to put right here, then you're finding this area and you're stopping it at x. And later, if you want x to be 1 or 2 or 3 or 4, you could plug that in. But for now, x is the variable. So because I'm already using x as the variable, I can't use x as the variable again, because then I'd be using x in 2 different ways. So I have to pick a different letter. I'm going to use t. So the function I'm talking about is t squared. Now, because the derivative and the integral cancel each other out, we should get the original function back again as our answer. To actually show how that works and why that works, take the antiderivative of t squared, that will be t cubed over 3. Evaluate that from 0 to x. And then last thing we'll do is take the derivative. So then substitute the top number first. That's going to be x cubed over 3 minus 0 cubed over 3. And then this is just 0, so that's already gone. Now take the derivative of this, which is going to be 3x squared over 3. The 3's cancel, and you get just x squared back. So not only does it give you the square function back, but it makes it a function of x. Now we need to do one more. Number 8. So how about if you are going to take the derivative and then you integrate, and then I'm going to use t, so it's t squared, and then it goes from 0, and at this point you think, oh no, he's gone senile. He doesn't realize that he just did that exact problem. It's because I'm going to change it. What if up here you put something besides x? You put 9x squared. So how is that going to change the answer? So the only difference between the two is this one just went to x, and this was t squared, so basically it just becomes x squared. So what happens if you have something more interesting up there instead of just an x? So first I'll do the antiderivative. So it's going to again be t cubed over 3. Evaluate that from 0 to 9x squared. So this derivative part, that's going to be the last step. Now substitute 9x squared in for t. So 9x squared gets cubed, and it's over 3, minus 0 gets cubed over 3. Now take the derivative, and I want to just leave it like this. I'm not going to simplify it because I'm trying to make a point here. So go ahead and take the derivative. This, of course, is 0, so that's gone. So the 3 goes over here, and you multiply, and then subtract 1 from the exponent. So these 3's are going to cancel, and it leaves parentheses 9x squared is squared. Don't forget, we're taking the derivative. So we did the derivative of the outside function. Now you need to do the chain rule, the derivative of the inside. See, that is a little more complicated than the last one. So if you wanted to be able to jump from here to here, well, then you have to realize that this is going to become the squared function, so it does, but you also have to plug this in, and you also have to do the chain rule. Okay, let's do one more like that and see if we could do it in one step. Example number 9. So how about we're going to take the derivative of the integral from, so the bottom number, I could put 13, 1, 0, 12, whatever. That part doesn't matter because it's going to be a number. When you take the derivative of a constant, it's 0. But then this part is what makes it interesting. So what if it is the square root of x? So what's the antiderivative of tangent inverse? Yeah, me neither, I don't know. I know what the derivative is. It's 1 over 1 plus x squared. What's the antiderivative? I don't know. So consequently, we're not going to be able to do it this way. We're going to have to just go from this to the answer. So whatever the function is, you get that function back, but you also have to plug in whatever this limit is, and you also need to do the chain rule. Let's do it. So you're going to get this function back. Oh, that should have been a t. Small technicality. Minus half a point for Greg Perkins. So you get this function back again. That's going to be tangent inverse. Then you're going to need to substitute in this. And then you're going to need to do the chain rule. So the derivative of square root of x is 1 over 2 times the square root of x. And there it is.